Hi, can you hear me? And how's the sound quality?
Good evening. I can hear and sound quality is very good.
Okay, great. So I suppose we can wait for some minute for others. I
Sure.
really hope that your classmates will join us. And maybe while we're waiting, so maybe you took a look on the file we created previous time, and maybe you even maybe tried to implement another certain algorithms.
Well, I was just looking for the URLs you posted, like a bubble sort and other sortings, and didn't try to implement the code yet.
Okay, okay, that's clear. All right. So I think that we can just take a look on other things. I mean other methods which we didn't have a time to implement. And if I'm not mistaken, I will share my screen. Um, yeah. So I suppose the screen can be seen now.
Yes,
Can you see the screen?
yes, we can see it.
Okay. Okay, great. If I'm not mistaken, by the schedule, it's like we have the pre-last class, and the next will be on the next week, and that will be the last one. And if I'm not mistaken, I will give you a definition of a project you will have to create before the 5th of January, and then on the 5th of the January, you make presentations about um, about your projects. Yeah. So and moreover, according to what we have our certain algorithms, which, from my opinion, well, in my opinion, we have to take a look on at least few of them. Have to be um, used, have to be understood, and then next on the next time we'll definitely take a look on OOP inheritance. Because anyways these two things, those are kind of must have for programmers. And actually it's not only related to Python, it's just overly, but since we are working with the Python, so we have to have and you have to understand implementation in the Python. All right, so let's take a look on things which we created the previous time. So we had this sorting file one, and since I'm gonna to, make an update and give you the file, so I will maybe make sorting file two, and let's take a look at what we did previous time. And actually, it was, if I'm not mistaken, it was kind of a kind of preparation for running search and algorithms and certain algorithms. So we had the random, we had some array, we had probably the value which we're about to search. Then the steps is for calculating how many iterational steps we've done for sorting, for searching. And then we had the binary search, which is the fastest search for sorted arrays. Well, for unsorted, as you understand, it's just going through the array until the moment you find a necessary element, or maybe one of necessary elements, or if you have a series of elements you're about to find. Well, in this case, in most of the cases, you're going through the array fully. which is super not optimized way. And clients who are using the software with such implementations, well, I suppose they would be angry. Okay, well, what did we have? So we created the array, we found out the maximal value, and we're about to look for that. Then um, we searched for an element. We found that in such amount of steps, which would be random, actually. Um, yeah, well, because it depends on exact values of the array, and then we had the brutal sorting method, which is the worst, I would say, but we can work on that. So it has its own iterative price, and then we applying the binary search. Well, yeah. Well, this is interesting. So binary search in this case will be literally based on amount of elements in your array. So it will be a priori, since we are looking for the biggest element, which will be on the one end or another end of the array. Then this binary search will give you amount of steps, which will be a priori the maximum amount of steps for a specific sized array. So it's not based on the random chance. So we'll use this binary search for different methods. So let's take a look. What was this brutal sorting method about? So we went through the array sorting as many times as amount of pairs of elements we have in the array. Then we go through the array through each indexed pair of elements, which doesn't mean values themselves, but element indexes like 0, 1, 1, 2, 2, 3, 4, 2, 3, 3, 5, sorry, 3, 4, 4, 5, and so on and so on. Yeah, we calculate how many such iterations we will have. Iteration can involve comparison and swapping of values, optionally, and we have its price. Okay, let's see how that works, because we have to refresh in the mind how this works. So let's take this link. Let's go by this link, and let's go for the Python. Yeah, and I will copy the name of the file. Yeah, this one. Okay, so literally what we have. Yeah, so we have the array. And it just happened that value, the maximum value is in the beginning, which is kind of super lucky case, which almost never happens. So yeah, so let's take another one. Okay, so here we see already something more close to real cases, and we had, if I'm not mistaken, some let me count, 30 elements. Maybe we can take a look on the variable, but it looks like 30. Yeah, 30. Yeah, so nextly what we did, we sorted the array. We have a price for that in iterations, and this price is kind of huge, but let's see, if we apply searching method, like binary searching method for sorted array, so the price for looking for the maximal value will be 4 in place of 14 for unsorted case. And you see a difference is 10 steps, right? Okay, this one is kind of random, or kind of you have to be lucky to have some small values here, but you can never rely on that, because you can have even some more steps, like 21. But okay, maximal amount of searching using binary search method for amount of element equal to 30 will be 5. It's the maximal one. It can be less, but it cannot be more. That's why binary search is really, really useful and is used by a lot of developers. But okay, the difference between, for example, 21 and 5 is 16, right? And for example, you can divide this value, the price of the sorting, by that 16, for example, and you will find out how many times you have to at least search value in the array to compensate this price. So let's calculate that. So 841 divided with the difference between the searching steps, 16. So if your array is used for at least 53 in, well, let's round this up. So 53 searching times in the array, then this price for certain is reasonable. Otherwise, it's not so. But once again, your value which you're looking for can be even in the end of the array somewhere. And then it wouldn't be like a 16 difference between them. But let's suppose it's the last one, and the last one means you will go through the whole array. So amount of steps would be 30. So a difference will be 25. And if we would divide 841 with 25, this would be already, well, rounding up, it will be 30, 34 searching times. So as you see, this values varies, but a priori, you know, we never receive data from a database or from whatever other source just to go through those data only once. It never happens in most of the cases, I would say. So the biggest question, well, is this price is really reasonable? That could be the question. And actually, it's reasonable anyways. But how many times we're about to use the array? That could be the question. And based on different methods, we can reduce this amount. For example, a bubble sort. Okay, we have this brutal sorting method, which is pretty nice. And node offsets, it works well. But what's another way? So we can take a look on this bubble sort. Maybe I have to turn off the editing mode just to be able to select link. Yeah, the bubble sort. For example, let's take a look on that. And here we will see some of videos. By the way, the video will be pretty interesting. So let's maybe take a look on that a bit. And we will apply things which I mentioned, which will be mentioned in this video in our algorithm. Okay, well, what's going on? Okay, let's take a look on this. Okay, why don't we have a sound? A good question. Okay, maybe let's go to the speakers. Okay, that's actually strange. So I will maybe use it in the macOS browser, maybe here. So why it's not going there? Oh, okay. Okay, let's take a look on this. Let's make this. By the way, guys, can you see it in the full screen mode?
Yes.
Is the screen still shared in this case?
Yes,
Yes,
we can
Yes
see.
or no?
Yes, yeah.
Oh, okay, okay.
again, there is no sound.
Wait a bit. Um,
Still no sound. So basically, maybe we can just try to watch on our computers.
okay. So sound is not going to you, right?
Yes, correct. No sound for us. No output.
Guys. Okay, that's a bit strange. That's a bit strange. Okay, anyway, so let's do like that. I will just post a link, right, in the chat, and this video lasts for um like a 3 minutes, right? So maybe we can wait for some 3 minutes while you will go the video through, right? And then we will program things. So once you will look the video till the end, please put a plus in the chat so I would know that. Let's do like that. Okay, so Vidas already took a look fully on the video. Okay, let's wait for others. Okay, Evgeny already made that. All right, so let's wait for Nikita and Thomas. And let's wait for Nikita. Okay, great. By the way, how it happened that you're only 4 in your group? Because I remember it was the time when you were 9.
I don't know. Maybe some of us already sick, or maybe just doesn't have time to join the lecture at this time. Sometimes, no.
Okay, but you see others that they are connecting to another classes, right? Or it's not so?
It's not so. One day we can see like one person, just a couple of them, like 2 or 3. Not every day we are like 9 or 5.
I think 9 is quite rarely. It's like
Okay.
five or 4
Okay.
people
All right.
in.
Mhm. Well, it is what it is, yes. Okay, so as you have seen, once we go through the area once, we already say that the last element which we are accessing through those pairs will take its solid state in the array. So if we have a scaled order like from the minimal value to the maximal value, on the right side, if we are going from left to the right, on the right side, after the first time going through the array, you will have the maximal element, and there is no necessity of making comparisons once again using that element. So how this affects our code? Let's take a look. Let's switch to let's switch back to our Windows system, and let's make a correction. So what I will do, I will just copy this code because we will have a modification of this one, and I will comment this brutal method code like this. So I'm doing that only with one ID, so you would have all of those methods in one file. And here we will make a small correction. So idea is super simple. By each next time we're going through the array, we have to go till for one element less, for one index less. So if our j, which is actually an index of going through the array, starts with the 0, so potentially we can take out a 0 from the first time we are going through the array, and next time we'll be going through the array, this j will become 1, and we can use that as something that's been subtracted from the last index, right? So if we have 30 elements, so we'll go first till element um, 28, because since we are taking low on pairs, it will be 28, 29. And next time, the last pair of elements will be 27, 28. And next time it will be 26, 27. So it will be in a such way. And literally, that's the only correction we need. And let's write, so price for bubble sort. If I'm not mistaken, it was written in a such, yeah, in a such way. Okay, so let's take a look what we will have in the result. So as you can see, here we about well, quite a flock, you know. So our value is lookable for well, within just few steps, I would say, which is not happening on the regular basis, I would say. Literally, we still have the sorted array, but let's take a look on the price for that. So it's almost 2 times less than the brutal method had. So you can see, right? And you can compare. It's almost for 400 iterations less for such sized array, for the array which contains 30 elements. Well, as you can see, quite interesting, and already you can say that, okay, to compensate this price, you will have to use array less than in the brutal sorting case. I think that's quite understandable. So guys, does it make a sense?
Yes, it does.
Okay, great. And let's take a look on one more modification of this brutal sorting method, which is kind of modification of bubble method. And that modification is called insertion sort. Well, in the jargon, we call this as stone method. So I will give you this link, so you could take a look on that on your computers. And once it will be done, please put a plus, so I would know that that we can start implementation of that. Okay, so I got plus only from Vidas. Maybe others took a look on the video as well. Okay, maybe we can wait for a minute and then we'll make implementation. Okay, I see that Thomas took a look on that as well as Evgeny. And we're waiting for Nikita. Oh, no, Nikita took a look on that as well. Okay, so literally, I suppose you understood why in jargon the method is called the stone method. So it's like bubbling going up and then goes down as the stone. Okay, so how is it possible to make a modification of previously created methods? So let's make a copy of this. And I will comment this method just to be sure you have everything in the file. Here. And how is it possible to make a modification? So the first of all is that we have to go through the array, comparing each pair of elements, and we go through the array in the primary direction only once, as you understood from the video. And what we have to do, we have to make a comparison. And comparison consists of comparing, in this case, j element and j plus 1. And if they are in correct order or not in the order you need, what you have to do, you have to make you have to literally make a comparison starting from j index till the index number 0, literally to the beginning of the array. Which means that if you have incorrectly placed elements, then what you're about to do, then you're about to go certain then you're about to go from element j till element 0 with the step -1. Well, give me a second, guys. I will try to check what's going on with the last value of the range. If we have a negative order of the value. Just give me a second, guys. Yeah, the last one will not be included as well. Okay, and if we taken for one element kind of less, like a forward, then we'll have one. Okay, that's great. That's great. So here we will go not till 0, but till -1. starting from J till this one. And actually, as you understand, once we need to swap these elements, they will be swapped through this comparison. And we will have to say that, okay, it's another kind of iterational action. So let's have a step increasing here and here as well. Okay, so literally that's the whole idea. And let's take a look what will be the price for this method. And if we will receive nicely sorted array. Well, first of all, let's take a look on the array itself. Well, it looks sorted, which is pretty nice. And literally, what's the price for that? Well, and price, unfortunately, in this case, is not really related to only amount of elements we have, but even it's kind of I would say dependent on values themselves, because once we'll run this few times, I mean this comparison, this algorithm, you will see that actually each time we have this different prices of certain of the array, but actually you have seen that values here could be really different, and okay, mostly right now they are around 400 plus something, but maybe you have seen that we had a case when it was like a 300 plus something. Okay, let's take a look, because we had one case here. As you understand, in a best case scenario, we'll have such many steps as amount of elements we have here only. But you have to be quite lucky to have it. So here we have that. So as you understand, this case is kind of based on what values we're having, but maximum amount of comparisons will be equal to swappings, actually. Swappings will be equal to amount of swappings in the bubble sort. So it can be less, but it cannot be more. And here keep in mind that we count the first comparison, then the second comparison going back as well. That's why we have this price, which is kind of a bit bigger than we had in the bubble sort, but it's not really really so. It's just amount of comparisons, literally. Okay, so that's the idea, which is quite interesting. I suppose this method could be quite clear, and we still have I would say a time which would be fine for implementing one another method, which is really cool, and I suppose what I will do, I can we can use the so-called HOR, so it has another name, quicksort algorithm. Here we will have quite fancy example, which lasts for some 6 minutes, if I'm not mistaken. If you like, you can take a look on that, but I suppose I can maybe show you maybe a few pages of a book that contains example. So we had some files here. Maybe it was here. Oh yes, it was somewhere here. Yeah. Well, this book is written in Latvian, but it doesn't really matter. Really, it doesn't really matter. So here we have a really nice example. So let's suppose we have the array, and you are about to sort that array using a so-called horse method or quick sort. What do you have to specify? You have to specify a range within the array which you're about to sort. And as you understand, we're saying from the beginning till the last element, we're about to sort. So, and you specify two indexes, first and last. Or maybe we can call them A and B. So, when you compare elements and they're located in the main idea of the method is that by each step we increase an element A or decrease an element index B. And after some certain amount of steps, comparisons, we can call that differently, A and B will be referring to one specific index. That would mean that element of this index is stored into the array, so it takes its place. And then we can take a look on the array on the left side of that and on the right side of that, if we have those arrays. That's the main principle. And from the beginning, it's assumed that if elements are located in necessary order, then we are decreasing firstly B index. And once we are swapping elements, like here we had 3 and 2, we're swapping them, so we start to modify index A. And once we will swap our values again, we'll modify index B instead of index A, and so on. So as you understand, this swapping of elements means a changing of index which will be influenced. And that happens within these things. So when this element took its place, then we overlook this part. So we have this value, this one. So this is A, this is B. As you understand, we have to swap them. So we become influence in index A. So index A increased, and this value took its place. And on the right side, it has none of the elements which are not stoned, and on the left side it has only one element. Okay, one element, what could be there? So next we're overlooking this area, and once again, firstly we are influencing index B, and here we don't have any swaps, so only B is being influenced. So we have this 4 on the left side. It doesn't have unstoned elements. On the right side it has. And once again, procedure is being just repeated. If you need, guys, I can share these pages with you if you will need that. But please inform me if you will need.
Yes, we need.
Okay, you need. Okay, then today I will upload them. Okay, so literally that's the principle of this method, and as I said, you can for sure take a look on this video. It's really fancy. Literally it has some again ads. Okay. So here there actually the dance which actually demonstrates this sorting, but you know, you can take a look on that maybe after the class. It's a really nice one actually. So I suppose it will be easy to remember this method by this dance. Actually I'm not kidding actually, guys. Okay, so let's try to implement this thing. So as you understand, guys, we have to have the array which will be sorted in a so-called templated way for each region of indexed values. How is it possible to be done? So well, first of all, since we're about to apply the same approach of sorting for different areas, then it means that we have to have probably a function that will run a certain algorithm for one region and then will do the same for two entire regions, or possibly two entire regions on the left and on the right side of the stoned element. So what I would do, I would say that we need something like a function for this purpose. So that function could contain um, index A and index B, for example, which would be a beginning of the array and ending of the array. And here, as you understand, the algorithm should work only in the case when A is smaller than B, because if it's not so, then actually A and B are referring to one element, and that element will be just stoned, right? So it will already a priori will take its place in the array, in the sorted array. So if A is smaller than B, only in this case, we're about to run our algorithm. And idea here is super easy. We have to have a switcher between these changes, like an influence of A and influence of B. A can be only increased and B can be only decreased. So we have to have some variable like maybe turn where zero will mean increasing of A, and one will mean, for example, decreasing of B. Okay, that would be great. Then we're about to do things. So as you understand, we have to make computations before the case when A and B become the same. So if A is smaller than B, then increasing A and decreasing B is the only way when A can be equal to B, right? So we can say that we can have something like a while loop, and we can have condition for running while iterations. So while A is less than B, so while it's so, because one condition is true, iteration will be run. When it's false, the loop breaks. So in the case when A is less than B, then we can have comparison. So if array, and we have our array actually, A element is bigger than B element, then we are about to swap them, as you understand. Swapping of them is super simple. We can just copy the code we used previously. So we have A, we have B. Into A, we write element from index B. Into index B, we write element from index A. Super easy, right? And once it happened, we're about to switch turn from 1 to a 0 and from 0 to a 1. Here, unfortunately, I'm not really sure if we can have something like in C++, turn equal to exclamation sign turn. So I will just make such comparison. Maybe even for you it will be a bit easier to understand this. So when turn is 0, then it becomes 1, and in other case it will become 0, right? So 0 goes to 1 and 1 goes to 0. And literally that's it. And in the end of this comparison, after the comparison, we have to influence A or influence B. And once again we'll have if, and if turn is equal to a 0, then we increase A. A becomes A plus 1. Or, and there is only one case when it's something else like 1. Then B becomes B minus 1. Well, literally that's the case. And we have literally one thing and another thing happening within a while iteration. Okay, so after it's done, so at what point a while loop can break? Only when a becomes equal to b. So they're referring to the same index. And if they're referring to the same index, we have to run the horse sort for the left side of that element and the right side of that element, as you understand. So we have to have horse sort for the left and the right sides. The only thing, guys, that here we have to mention the beginning of the region and ending of the region, which means that actually we have to maybe remember this a and b as old values. So how to do that? So we can have a old value and we can have the old value. So a is on the left, b is on the right, and a equal to b, they're somewhere in the middle. So the left side will be a from a old till a, and right side will be from b till b old. But since we are not comparing the element which is stoned, which took its fixed position, we are about to not take that element into comparisons. So we're ignoring that. So we're decreasing the last element of the left side, and we increasing the first element of the right side. Literally, that's the idea. Okay, so let's try to use that. Well, I will comment previously used method. And I will probably use steps equal to a 0. Then I will print the array after applying this function, and I will say that okay, I have a price for a horse sort, and this price will be counted exactly here on the comparison. Okay, and what else is missing? I have to literally run the function. Okay, so it will be from 0 till n minus 1, because n was 30. So n was the amount of elements in the array. Well, yes, that's the thing. And let's see how that works. I really hope that I wrote everything without problems. Okay, I really hope that. And let's run it. Oh no, looks like there are some problems. Okay, Marx is found. Oh, okay. Module. Okay, it might happen that I would need to use a global R to have an access to the array, and I will need to have the global steps to have an access to global variable steps. I think that's the mistake I had here. Yes, that's correct. So, do we have a sorted array? Well, yes, definitely we have one. And what's the price of that? What's the price of this method for such case? It's 146 comparisons. If we would try run this a few times, so you would see it could be even less. Well, how that happens? Well, because it's based on values we have in the unsorted array. Because once again, it's not only about the length of the array, it's even about elements we have inside the array. That's the idea. And now, if we would try to use the same comparisons related to how many times we need to run computations, which have a difference between optimized and non-optimized way equal to 25 steps, well, you will find out that actually this amount will be quite small. So like a 6 or 7 searches in the array will cover this price of sorting the array, which is pretty nice. So guys, does it make a sense? Is this algorithm clear for you? If you need, I can give you some half minute or a minute to think about this. Oh, plus minus. Okay, plus minus. All right. So once again, we have the beginning of the array and we have ending of the array. Anyways, we have to compare elements from both sides, and after each comparison, we are moving indexes forward one to another one, and we are moving index A or index B. A is the beginning, so it's increasing. B is the end, and then it's in decreasing. And it should be done all the time after a comparison. And once and from the beginning, we say that we're decreasing index B. So once we have the case when we need to swap elements, we say, okay, we're switching from B to A. And once when we influence index A, we have something to be swapped, then we say, okay, we return to index B. And that happens all the time. But once again, maybe I can just share these pages with you. Oh, also, these pages will be available in the recordings anyways. But I will just upload these things anyways. Yeah. So that's the principle of this. So like we're overlooking the full region, the full matrix. So firstly, we say after comparison, we're decreasing index B. So we compare them, nothing is swappable, so we decrease in index B. So it becomes not the last, but pre-last. So we're comparing them, nothing's changeable, they're in the correct order, so we decrease the index B. 3 and 2, we have to swap them. So we're not working with index B anymore, we start to work with index A. And once we swap them, so we increase index A. And we compare 1 and 3, they're on the correct order, so okay, we keep increasing index A. So here, do we need to swap them? Yes, definitely. So we're swapping them, and again we are influencing index B. So index B will be decreased. Here, everything's fine, so index b is decreased. Everything is great, index b is decreased. Everything is pretty cool here, so once again, the index b is decreased. Everything is excellent here, so index b is decreased. Everything is marvelous here, so index b is decreased, and a became equal to b, and then the story will be the same for a left side on that element and for the right side of that element. The story will be the same. That's the main principle. Did it become more clear? Okay, that's great. That's great. Okay, so I really hope it's understandable for you for now why we need to sort elements in the array. What is the difference between those methods, which we had a time to overlook, and how is it possible to implement them in the programming language we're using, so in the Python? Okay, so we have a few minutes left, so maybe it's a time for Q&As, maybe some questions from your side. Okay, I suppose silence means no question. All right, so as I thought. Okay, all right, guys. So as I told you, next time we'll take a look on inheritance of objects of classes within the Python, and I will and we'll have a small talk about a project which I will be waiting from you on the, if I'm not mistaken, 5th of January. Let's take a look again when it was planned. Yes, the 5th of the January. Okay, guys, so thanks for being connected. I hope you liked today's class. Well, the only thing you have to maybe try to use these things, but it's just a matter of practice, I would say. All right, so once again, thanks for being connected today, and see you next time. Bye-bye, guys.
Okay, thank you. Bye.
Bye-bye. Have a good evening.
You too.
Thank you. Bye.
You are currently the